Welcome. Thank you for joining us. Today we have Bill Hoffman from Kitware talking about the cool work they've been doing on open source build systems for C++. So without further ado, Bill.
Thank you. Okay, my name's Bill Hoffman. I'm from a company called Kitware, and I'm going to be talking about CMake, CPack, CTest, and CDash. And these are open source tools. Anybody can use them to build, test, and deploy software. C++ was the main target, but we can do other software as well. So here's a quick overview of the talk. The first thing I'm going to talk about is Kitware itself, just a really short introduction to give you an idea of what the company is and what we do. And then I'll get into CMake and the build tools. So the company was founded in 1998. The founders are 5 previous employees of GE Corporate Research and Development. And it's a privately held company. We've never had any debt, so we sort of bootstrapped the whole company, one contract at a time. This year, I think we'll hit about $14 million in revenue. We do principally consulting and grants with some product revenue. But we're basically sort of a research shop. People can outsource the research, and we're really heavy into open source. We have about 65, 70 employees right now. We've been growing about 30% every year. There's about 25 PhDs in the company, a lot of master's level, very developer heavy. In fact, I think for the first 5 years, we had a part-time administrative person, and that was pretty much it. I used to run QuickBooks for the company. That was fun. I was an accountant for a while. Okay, so what do we do? What do we do all this? Lots of hats at a small company. So what we've evolved into is what's on the screen here. This is our splashy marketing PowerPoint slide. So we do supercomputing and visualization. So we do a lot with national labs, Sandia, Los Alamos, and our roots are really in visualization. The visualization toolkit, VTK, was really the core of the company. It's a C++ toolkit for developing visualization applications. We've done a lot of work there to create parallel visualizations so we can do things with render clusters. So they might have a 100-node GPU available farm plus a 1,000-node computation cluster, and we can drive that from a desktop and do rendering and compositing back in the desktop or even over the web. And then we've also got a real strong medical imaging group that does some interesting stuff, doing segmentation and registration work with medical data. And we've also gotten a little bit into the data publication area where we can take these large data sets, either supercomputing visualization data sets, medical data sets, and store them online, get to them with databases, and then write applications to visualize them. And in the past couple of years, we started a computer vision group as well, and they mainly work in wide area persistent surveillance, so video recognition, tracking people in videos. And really, all this is tied together with our software process tools that we've created that are open source that I'll be talking about. So here's a quick slide of the workflow that we've created. And the idea here is that we've got developers, they write their code, they check it into their version control system of the month, Git, SVN, CVS. The idea is, whatever version control system they're using, they check it in, it goes into a repository, and then it goes off to a testing farm that pulls the code out of the version control system and then sends that data to a web application we call CDash, which is a PHP, MySQL, LAMP stack application that can display the build results. And this really came out of GE's Six Sigma push, if you can believe that. Six Sigma was this effort to, I think Motorola started it, where they try to get the defects in really large manufacturing issues down to the Six Sigma, the standard deviations from the norm. So you want really few defects. And if you've got a big company like GE and you want to push an initiative like this, and you're Jack Welch, you just say, well, everybody has to do it. From the administrative staff on up, everybody had to take training in this. And we were researchers at a research center. We wrote a lot of research code that you throw away, and it was like, how's this fit us? But some of us really like software, and we like software quality, and came up with this idea of creating, well, what can we measure in software? What sort of defects can you measure in software? Well, you can measure things like number of build errors, number of build warnings, number of test failures, test timings. Does it change over time? Is the software getting slower or faster? And then create a dashboard and a way to look at these things. And that's what this system does. And I'll be talking about these tools. So a quick overview of that part of the talk. First, I'll talk about building with CMake and what the actual CMake build tool does and how it works. And then I'll follow that up with testing with CTest and CDash. And finally, we've got a packaging tool called CPack, which can create installers from your CMake list files that describe your build and install tree. So CMake. This is the CMake section. It's a cross-platform build system. And I'll be talking about why you'd want to use CMake. I'll cover some of the cool features it's got and just basics of how you would use it and how you'd write an input file for it. You can get help. We've got a book we published from Kitware called Mastering CMake. There's a web page, cmake.org. There's also a wiki and a very active mailing list. If there's any questions, I try to make sure they're answered. Some of the times I don't even have to answer them anymore. There's a growing community. Yeah. We do. I think so, yeah. Yeah. I think we're seeing a lot, and they can really help out with, we've got modules that find third-party libraries. So there's a whole module directory for, finding things from libxml to other things, and I really don't have. Yeah, well, to find software. So CMake, so it's got like a find the installed version of libxml on this machine. And I'll talk about that a little bit more, but they've been contributing a lot to that because I don't have access to all software. I don't use every software in there. There's hundreds of packages. And without the help of the community, that stuff would really not be as good as it is. So what is CMake? Or why CMake? Okay. It's easy and it works well. That's what I like to say. A build system that just works. And it's easy to use cross-platform. So this slide here shows a typical project. It's actually the curl project. It's an open source C thing for grabbing network activity, FTP, C URL. It's a pretty neat package and it's pretty common. And if you look in the things I've highlighted in red, that's their build system. So you can see there's a makefile and a makefile.am and a makefile.in, an AC local, a build conf. There's an install.shell and a recomp script. There's even a Visual Studio 6 DSW file, something called maketgz, make installers. And then down here they've got a makefile for Watcom, Borland, AM, NetWare. You get the idea. A lot of stuff. And I guarantee you, at any one point in time, all of those aren't going to be working. What happened with the project? Someone came along and said, hey, I'm using curl with NetWare. And I've got this makefile. Can I contribute it to you? And the guy's, sure, yeah, cool. We'll throw it in. And this stuff, if it's not tested and not tried every day, it's probably going to break. Someone's going to get a new version of that compiler. And in the light blue there, that's what it requires to build it with CMake. So there's a CMake list file up at the top, one at the bottom. There is a directory that has like one or two module files, but it's really small. And what this allows that group to do is outsource this maintenance of all these different things to the CMake team. So they can not worry about how to generate a NetWare makefile. If CMake supports it, then the CMake team is going to worry about it. And the CMake team is going to worry about it by looking at the dashboard to make sure that it's still supported. And once it's supported, it's always going to be supported as long as we run it on the dashboard. So another reason to use CMake, it's fast. We try to make it as fast as possible. This is a blog I found off the web. It was a Quantum GIS code base switched from AutoTools to CMake. And their overall build went from about 22 minutes to 12 minutes. I think the large part of the improvement here could be the not using libtool, which is essentially a shell script, which on startup basically has to figure out everything there is about your platform, and it's got information for all the hundreds of platforms it supports, and has to trace through all that stuff every single time it goes to create a library. Whereas something like CMake generates a static makefile once for the system, and then every single library that's built in the system just happens as fast as possible. Why use CMake? Everyone's using it. So in 2006, KDE switched over to using CMake as their main build system, and the KDE desktop for Linux. And this is a Google search trends that I like to show. And you can see we didn't really even show up on the map, although the project's been around since about 2000. In Google search trends around 2005, 2006, when the KDE guys started using it, people started saying, well, what is this CMake thing? And we've grown quite a bit. There's about 1,200 downloads a day from our website, but it's also distributed with major Linux distributions. Cygwin provides CMake packages. Some big projects use it. KDE Second Life is using it for their build system. Boost is using it experimentally. We're working on moving that onto their main system, and lots of other projects. So what is it? Drink here. It's actually become a family of software development tools. The first one is CMake, which does the building. And the second one is CTest CDash, which does the testing. And finally, there's this C packaging tool. And it's under an open source license. It's a BSD style license. The history actually comes from the Insight Segmentation and Registration Toolkit. This was an NIH funded effort. Is anybody familiar with the Visible Human Project? No? Yeah? Okay, so Dan is here. So the Visible Human Project was a pretty neat project that NIH put on where they took a human body after they died, and right after death they CT'd them, MR'd them, PET scanned, every modality they had at the time. And then they froze the body solid and sliced it up as thin as they could and took actual pictures. And this gave a really good data set because if you've ever done anything with segmentation or registration, it's really hard to get ground truth for this data. If you just look at a CT scan, I mean, you can't really cut someone open and say, did I get it right? With this data set, they can. And they had collected this data set, and that was great for science. But the next step was to help with the algorithms for that. So they've got this public data set, and then they wanted to create a public repository for algorithms. And it's written in C++. It's got quite a wide user base now, and it really advances the state of the art in studying with that type of research in registration and segmentation. And we were part of the lead engineering team for that project. And I remember giving a talk early on in the project. I was presenting my ideas, and one of the guys from Pitt raised his hand. He says, Bill, why are you creating this build thing? It's going to be the ITK build thing. No one's going to know it. No one, what? Before he finished and let me answer you, whoa, wait a minute. You're not talking about changing the way that people build ITK. You're talking about changing the way people build C++. I'm like, yeah, that's it. That's what we want to do. So that was a while ago, and we're getting closer to that. So but now I'd like to talk about what I mean by that. So how do we change the way we build C++ with CMake? So I saw a really good talk by David Abrahams. He's one of the lead Boost developers. And he showed that Boost, explained what Boost tries to do, and he had a real neat slide. He put it up there, and he says, here's Java, and here's all the classes that come with it. There's a network class, and there's just tons of classes, hundreds of real rich feature classes. And here's Python, and here's all the really cool stuff that comes with that. And here's C++, and we got an IOStream library. Kind of boring. And then a lot of extra stuff. So, and even STL was added in sort of at the last minute. I mean, it became part of the standard. It really wasn't vetted by any community. And Boost aimed to fix that problem for C++, to give the community a place to try the next things that are going into the standard. So when the next C++ standard comes out, the new innovations from it, most of them will come from Boost. So Boost aims to give C++ a set of useful libraries. CMake aims to give C++ compile time portability. We can't do the compile once, run everywhere, but we can certainly do compile it with one input file and run it, build it everywhere as easy as possible. And it really makes it easy to build a small tool that links to a large tool, which is one of our goals with ITK. So we created this huge C++ library, and you want the researcher, some grad student, to be able to pick it up and link it into his application really easy. And you can see, so I've got the pictures down on here of all the different platforms. So we go everything from supercomputers all the way down. I saw a blog of someone describing how to use CMake with the Nintendo DS. So, and interesting thing, the supercomputer probably has a lot more in common with programming on the Nintendo DS than the desktops, in that they tend to, a lot of them, like the Craze or something like that, have very minimal operating systems. They don't have shared libraries, and you have to cross-compile to them. So CMake's got pretty good support for cross-compiling as well. So you can write your stuff and have it build on any platform. So who's involved? There's a whole bunch of users. There's KDE is one of the bigger, more well-known ones. Second Life is using it, ITK, of course. VTK, our visualization toolkit, ParaView, numerical package from Sandia Labs called Trilinos, Scribus, Boost. MySchool's using it as its build system. Currently using it just for Windows, although I saw something on their list where they're, why aren't we using this on Unix? And I think they're moving that way. LLVM, which is the next, are you familiar with that? Yeah, that's sort of the next big thing coming in C++, open source compilers. Apple's working on that, and they're using CMake as their build tool. And this list on the right are the supporters. Kitware, of course, is very interested in keeping CMake going. Army Research Labs, National Library of Medicine, Sandia National Labs, Los Alamos, the NAMIC. So the idea to show this slide is just to show that there's support behind it and there's funding going into it. So it's not a stagnant project and it's not a hobby project. There's probably 3 or 4 full-time developers actually getting paid to work on CMake and the CTest and CDash and the whole tool suite. So it's here to stay and it's got some legs. So the documentation, we've got the book you can buy. We're working on the next version of the book. It's going to be out in the beginning of the year. It's the web page and the wiki and the mailing list. There's full reference documentation online. It's generated from the code itself. It ships with HTML, man pages, command line help. There's a nice tutorial that's included in the testing tree. Test tutorial, we try to test everything we do, even the tutorials. You can create configured files with CMake. You can do optional build components. It's got good support for install rules and doing test properties. You can do system introspection, check for the exists, so you're not programming to a particular system, but more to a canonical system. You can, instead of writing, if Apple in your code, you can say if this feature exists. And then it's also got this packaging tool called CPack and CTest and CDash. So some of the features, there's one simple language for all the platforms, works on Windows, Mac, Linux, all the Unix variants. HPC, high performance computing, or embedded platforms via cross-compilation. We had this slide here, we did ParaView, which is our visualization tool for high performance computing. And we needed to run it on a Cray XT5, I believe. And we wrote the cross-compiling part of CMake for that project. And it uses Python. And Python's build tools, we looked at the build tool, tried to get it to work with the cross-compiler. At the end of the day, it was easier for the developer working on that to just write CMake files for Python. And I think he had it done within an afternoon. He had it cross-compiling. It generates native build systems, so it's not an actual build tool. It's a meta build tool. Right now, we generate makefiles for GNU Make, NMake, Borland. We do Kdevelop, Eclipse, Visual Studio 6 and up, including the beta, the 2010 Xcode projects. This next slide is really important, I think. We handle out-of-source build trees very easily, so you can just make directory build, CMake ... point it back to the source tree. So on my laptop, I might have 3 or 4 compilers installed, and I'm running off the same source tree and doing a build with each of the tools I want to test on. There's interactive configuration via graphical user interface written in Qt. It supports multiple configurations, debug, release, etc. There are built-in rules for the common targets, so creating an executable is just a real quick command. Creating shared libraries or DLLs cross-platform. Creating static libraries or archives. And we also have good support for the Mac or the Apple. We can create OS X frameworks or application bundles just with one extra little bit of markup in the library definition. But if that's not enough, we can also do custom rules. Now, part of what we did going back to VTK days, we've always had our C++ automatically wrapped into other languages. So VTK since before 2000 has had, 94, has had a C++ parser built into it that parses just the header files and then outputs into Java wrappers or Tcl or Python wrappers. So we've always needed a complicated build system that can handle the concept of building some code, which would be the generator, then later taking that executable that was built and then running it on part of the source code for the project, generating more source code, and then compiling that source code. Getting that to work with, say, something like a Visual Studio project by hand is somewhat tedious and error-prone. With CMake, you create a couple of custom commands, and then it's going to work across all these platforms I talked about. It's going to work in Xcode. It's going to work in all the Visual Studios. It's going to work in makefiles. So it gives you, it's got a lot of power there. And it's also got configuration rules for doing system introspection. It's got its concept of persistent variables. These options can get cached. So I really don't try to avoid the concept of environment variables. See a lot of projects where, to build this project, set these 5 and 6 environment variables, and then type make. And if you forget to set them, or maybe you set them the first time you type make, and then you go to a new shell and they're slightly different, and you type make and things start blowing up and you're scratching your head going, what happened? When CMake finds something, those find package I was talking about earlier, it stores the location in a persistent cache file in that build tree. So you can have the multiple build trees, they can have different configurations, different things they found, and it's all stored there, and it's not stored in environment variables, and it's not going away, it's tied to the build tree. No, it's not. Yeah, it caches it once it found it. And then you can go in with the cache editor and remove it and have it find again if you want it to. But again, it's there for performance as well. It also has a really good implicit dependency generator for C, C++, and Fortran. A lot of the supercomputing folks are still writing a lot of Fortran. They're even writing new Fortrans, Fortran 95 and stuff. And Fortran actually has this module system, which is sort of like Java, I think is what they stole it from. But it makes it a real bear for a build system, because essentially what happens is instead of just saying you include foo.h, you say use module B. All right, well, you never write b.h. When you compile B, it spits out b.mod. So the compile order is important. If you compile A before you compile B and A uses B, it won't compile. So originally, one of the guys at Kitware converted was a chemist or physicist code, old Fortran code, and he said, explaining how to use it, and he said, you run CMake and then you type make. The guy ran CMake and you type make, and he went, it's built. I only had to type make once? Usually I take it 4 or 5 times, because that's what these Fortran guys do. Anyways, we do dependency analysis, and this also is real important for developing, because especially with C++, if you have a header file that's out of date with the source file and your build system lets you down, and you've got one object file that thinks a class is 100 bytes and another one thinks it's 104, you can get really weird bugs, and you walk into the debugger and you're really scratching your head, and that kind of stuff can waste hours of developers' times. Yeah, it handles that. Yeah. Fair question. We use CMake actually in the make files at least at build time. So make will call back on CMake to have it do some dependency analysis. And also when you create those custom rules, you have to describe your inputs and outputs. So we know something's going to be an output, and then when we're scanning for dependencies, if we see one of those outputs show up as an input in a regular .c file, it knows then that that's coming. And it does sort of a multiple recursive make kind of thing to make sure that everything happens in the right order. we do call back into it from other environments as well, when we need to. So it can get around problems. And so for instance, in Visual Studio, if you change a CMake list file, it will notice that when you say you try to do a build in Visual Studio, it'll say, hey, look, the CMake list file changed. It'll rerun CMake, and then CMake can actually, it'll go back and detect a running Visual Studio and see if it matches that project. If it does, it actually loads some macros that keep it from saying, reload, 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 reload. It can have it do one reload and resume the build. So we've got some Visual Basic plugins. Yeah, we haven't had to do it with Xcode in that, yeah. Okay. We also handle link dependencies. So inside your project, you can say, add library B, and then you can say library B links to C and D. And then if you create an executable, you can just say, link to B, and it'll pull in the other dependencies. And it makes it easier to handle large, complicated projects. We also support ordering of link search paths and building R paths into executables. So you can run out of the build tree without having to set load library paths. But then when you do install, it can actually rewrite the R paths, and it actually edits the ELF, so it's fast during the install. It also has really fast makefiles. It does nice color output. You can see on the slide here, it's got different colors for different types of builds. So C++, building an object shows up in green, linking something shows up in red. It's got help targets. You can type make help. It'll print out all the targets. You can do things like make foo.i. It'll pre-process it, and it'll handle that cross-platform. You can do assembly targets as well. The input to CMake. So what does it look like? It's a simple scripting language with built-in commands for common rules. So here's an add library, mylib.cxx, or add executable. And this bottom example here shows sort of the power of this. So I'm in 6 lines. I'm saying that I'm telling it which CMake I want to use. I'm giving it a name of the project, and then I'm saying find package boost required with threads and signals. And then I'm telling it to use include directories, $boost include dirs. And then I'm adding executable, my executable, with some C++. And then I'm telling it to link to the boost libraries. And that's going to work on the Mac. It's going to work on Windows. It finds the installed boost. If it doesn't find it, you can tell it where it is by editing the cache through our editors. If it's installed in the usual location, it should be able to find it. So installing CMake. So one of the things that the biggest roadblock to adaptation of CMake is, well, gee, now I have to depend on CMake. So we try to make it really wicked easy to get CMake and install it. So on CMake.org's download page, we've got binaries for every Unix, I don't know, 5 or 6 Unix, like HP and IRIX even. And we get 3 or 4 downloads a month or something for these weird platforms, but we do it. Yeah. And also the major Linux distributions these days, especially with KDE's adoption, you can usually just say apt-get CMake. But we provide the binaries for all the platforms, and we'll keep doing that. Installing it, you can grab a Windows binary installer. There's Linux binaries. And the source can be bootstrapped on any Unix platform. So this is really what the process does. So when it configures, it will read the cache file that I talked about, if it exists. Then it will read the CMake list files, and they can include other CMake list files and have subdirectories. And then it'll write the cache back out. And this can be an iterative process because you might be you can imagine a thing where someone clicked an option that said, use MPI. Well, now it's got to find MPI or enable parallel, and then it turns something on and it exposes some other option. Once you're happy with that, it'll write out the makefiles for projects. And these are what the editors look like. There's a graphical one written in Qt that has nice little buttons and stuff to click, turn things on and off. And there's also a curses-based one if you don't have a windowing system. And of course, you can run it from the command line. People get scared. They say, "Oh, do I have to run a graphical thing to build my tool?" No, no, no. You can run from the command line if you know the exact options you want, and you want to automate a build. Or a lot of people use it like this. It also has some. You can write scripts in the CMake language. And CMake has some simple commands like CMake -e, things like copy, remove a file, compare, get the time. And this is so you could imagine building up a whole nice cross-platform build system and then calling CP in the middle of it. Well, that's not going to work too well on Windows. Right. Right. So the only thing we want to require is CMake. And the only thing CMake requires is a C++ compiler. So if you've got a C++ compiler, if you're building C++ code, you figure you have to have a C++ compiler. So that's our minimum requirement, is a decent C++ compiler. And you can grab the binaries. But we build this in, and that's why I'm saying that CMake is actually called by Visual Studio, by a lot of projects, to do these sort of cross-platform things that aren't easy to do cross-platform. There's also a scripting language. You can do it, CMake-P, and write CMake language, and it wouldn't generate a cache. It ignores commands specific to building, like add library or something like that, if you want to do something a little more complex. But again, we want to try to avoid having dependencies on other bigger systems. Okay, that sort of wraps up the CTest CDash part of the talk. I mean the CMake part of the talk. Whoops. And we're on to the CTest CDash. So this slide here is it's actually a pretty old slide. It's from a book from 1999, and it's showing the benefits of automated testing. So it's showing over time that if you did a little bit of a long test case, but say you had a test case that took 45 days to complete each manual retest. Over a decade, your manual running those tests every time you did a release is going to cost you about 97% more than if you had some push a button and have it go. Kind of goes without saying, but it's nice to show people this. And a lot of software that's out there, especially open source stuff, doesn't necessarily have as much rigorous testing. And our system is built around that. I mean, the developers, we didn't want to create a system that was overly intrusive. And it's an easy system to use. It's easy to apply on projects, and the developers actually like it. I mean, we've had interns come on and do code coverage, which sounds like a really boring job, but it's really neat when they can watch every day. They can see their progress. They can, hey, look, I got it to go from 75% to 78% today by adding these tests. So it gives them something to look at, something to work toward, and it's neat stuff. So this video here, let me show this. This is running a nightly regression test of ParaView. And we've recently added into CTest the ability to do parallel. So you can say CTest minus JN and run. This is running on like I think an 8-core Windows box. And it's doing a minus J8 and running our application here. And this is doing screen captures in the background and making sure the images look like what we expect. And this stuff goes on every night at Kitware on a bunch of different platforms. And we can take advantage. We're trying to make it scalable, so it'll take advantage of all the cores that are out there. Yes, you can add test dependencies. So that was one of the first things. We added this, and then you run an ITK and you say go, and like, gee, why did these 50 tests fail? Yeah, that actually happened with ParaView. Yeah, the test case opened up a socket and testing client server. So you can add dependencies on the tests, and it'll make sure that it blocks until they run. You just say you can only put dependencies on a test, like test name depends on some other test name. Yeah. There's a flag there's a property you can set on the test that says I need to be run by myself, but you can also say I need to be run after this test, because a lot of times people write a test suite where the output of one test is used as the input to the next test, and they just assume that they're going to run in linear order, and you can set up that dependency as well. But if you've got ideas too, I'm open to ideas of adding new stuff into it as well. The executable, so to create a simple test, you write add test, you give it a name, and then some executable to run and some arguments. It's expected to pass if it returns 0. You can also set it up so that it'll pass based on some regular expression matching of the output. Not flakiness. You can set expected to fail. Yeah. Although that's a really good idea because we've got some tests like that as well. Yeah, no, that's a really good idea. And we've actually got a few of those tests in CMake. I think right now the packaging on Apple for occasionally just doesn't work. Yeah. Right. All right, so to run the test, you run, there's an executable called CTest, which is delivered with the CMake binary. And it can run either for this continuous integration testing, which I'll get into how that works, as a client for CDash, or you can just run it from the command line. You can type CTest before you check code in. It can be used on CMake-based projects or even not CMake-based projects if you wanted to. So here's the dashboard that I've been talking about. If you look, let me see if I can get this. So down this side here are the build names. So the neat thing about this testing system, I think, is that it's very easy for outsiders to contribute to it. So oftentimes, someone might come to me and say, hey, can you port CMake to this? And I go, well, yeah, if you'll run a dashboard, because otherwise I'm wasting my time. We had a guy, there's a guy down in Australia that uses QNX. He's using VTK and QNX operating system. He does these room-sized robots that do mining in Australia, in the outback. And he's a big CMake fan, and years ago, he came to me and said, hey, can you get CMake working on QNX? I said, sure, if you'll run a dashboard. And he's been running a continuous and a nightly dashboard for years now, and I've actually developed stuff for QNX by checking in code with a couple print statements, if def QNX, wait 5 minutes, look at his results. I'm like, that's what it's doing on that platform. He's different time zone and everything, and I've been able to work with it without even bothering him. And the nice thing is I know it's going to keep working. As soon as it's off the dashboard, we're going to break it if you're not testing it. So anyways, down this side is the site name over here, and you can pretty much pick that. Some are Kitware, some are not. This is a build name, so this one is it's a Linux 64. There's a Darwin, which is a Mac, another Linux 64, another couple Macs. We've got a style checking test that checks the C++ coding style. And then over here, it's got the update column, which is what files were updated from the version control system. There's a master one up here. You can look at the nightly changes. This is just what happened when it... And the nightly builds actually pull from you set a timestamp. So you say 9 o'clock Eastern Standard Time is when I want my dashboards to run. And then a CTest client looks at that configuration file, and it pulls from the version control system a copy of the code that matches that time. So each one of these is testing the exact same snapshot of the code. You can set it up to do revisions, yeah, if you want. But the nightly idea, even if you're on, say, a branch, you want to still pick a specified time. You can also do experimental builds, which are just any random thing that pumps up. And you can also do the continuous builds, which are set up to run as soon as something's checked into the repository. Yes. Yeah, you can tell it to remove the whole binary tree if you want. Usually you do an out-of-source build. And then you can set a flag that'll do clean build tree. And we also support big complicated stuff. This was a project we did with Sandia National Labs. And they have a project called Trilinos. And the idea here is they have about 42 sub-projects. And they've got teams of people working on each one of those sub-projects. And the guy who's working on Tethos or ePetra, he doesn't want to hear about the problems in Zoltan. He doesn't want to get emails from the dashboard system when Zoltan guys break something. He doesn't care. And it doesn't affect him, but again, someone might care about all of Trilinos and want to be able to see it as a whole. And we created this concept of sub-projects in the dashboards so that the Tethos guy can set up, I want to get emails when anything bad happens on my project and not when anyone else has something. So it can be used to scale to really large projects. It also supports these query filters. So you can set up either show filters or hide filters, and then you can do things like, show this build name matching this over this date range. I want to see this particular platform for the past 5 days, and it'll show all the builds for that. Or even I have a custom one that shows me basically all the errors. I can click on it. I save it as a link up top here. I think yeah, there it is. I've got it saved as a link up here in my taskbar. CMake only errors. So I click on that, and it's a saved query. You can click on create a hyperlink from the query. It's all PHP stuff. Pretty straightforward web stuff, but it's nice stuff to have. Another thing we recently added, in prior versions of CMake, we always did essentially log scraping. And for some of the build tools, like Visual Studio, we still do log scraping, which is let the tool run and then have a bunch of regular expressions that pull out things that look like an error, look for error colon or whatever, which is okay, but you might, something like this particular one around here with C++, if you have one error, you're likely to have 50 in the file. And then what this does basically is you can stick into mode, because we don't want to pay the performance every time, but if you're building it as a nightly test, you can set it up in a mode where it'll essentially wrap each command in the make file with a CMake --, run the command, launch the command, and it launches it through that, and then if it returns a non-zero value, it knows it failed, and then it can store the standard error and standard output and show it in the dashboard as one single failure instead of lots of little failures. Again, this isn't supported across all the build tools we have, but at least on the make files it works. We also have coverage built in. So there's 2 tools right now that we support for doing coverage analysis. The one is standard GCov, and the other is a commercial tool called Bullseye, which does branch-based coverage, which is actually a kind of neat concept. Instead of just showing number of times a particular line of code was executed, it'll show if it's got a branch, like down here it's got an if statement. I don't know if you can read it, but it's got a capital F there, meaning that it was only ever false when it was run. And again, these tools are things that developers, everybody knows, it's good to do code coverage. And I think I ran GCov once. So CMake's essentially an expert system it's stored this information. It knows how to run GCov for you. You set it up, and then all the developers on the team can see their coverage without having to run the tool. It's run for them every night. You can watch the coverage go up and down. You can see it when new tests come. You can even have it send you an email when code, particular file is low on code coverage for the testing. And we also do the same sort of thing with Valgrind and Purify. So you can see, and again, these are tools. When do people run Valgrind? When something weird's happening, right? But it's not necessarily part of every developer's, before they check in their code, do they always run it? Maybe, maybe not. You don't know. With this, we know. We can say, when that showed up, when it crashed, we go right back to the dashboard. Why didn't Valgrind catch that? Oh, we didn't have good code coverage. And then you go back and you find out it wasn't covered, and that's why it wasn't caught. But again, these are tools that people know how to use, but they might not use it every day because they're busy. They want to get stuff done. And the sooner you catch bugs like this, the better. I mean, as soon as someone's checked in that bad, array bounds right or memory leak, if you can go back in this system, even if they didn't catch it, you can go back and see which files were checked in that day it's a lot easier to fix than if you're sort of scratching your head trying to figure out, gee, no one's run this for a couple months. And anyways, you get the idea. It can send you emails. This is a typical CDash email notification saying something like, a submission to CDash for this project CMake has failed test. You've been identified as one of the developers to check something in. And then it'll give you a link and a short little description. And if you want to try it, we've got hosted at Kitware. We've got cdash.org, CDash public. You can just click on there and say, start my project, and it'll create a CDash thing for you, and then it creates a configure file that you can drop into your CMake list, and you can get going with it pretty much right away. And it's all open source as well, so you don't need to use us. But if you don't happen to have a LAMP stack web server lying around, you can try this. Had the email know which tests failed? So when the client did a build, it created an XML file that showed which tests failed. Sent it up to CDash. CDash said, all right, these tests weren't failing. The last time I got a build from this machine, those tests weren't failing. For the whole process. So when I run CTest, if I'm doing a nightly or a continuous, it'll collect up all the test results and put them in an XML file. And each test has a name. So you can see here, like, system information new. That's a test name in CMake. Yeah. Mm-hmm. Well, there's two ways you can do it. One is an executable that returns 0, 1, or two, you can do some sort of regular expression matching in the output of the program. So you can say, set test pass regular expression or set test failed regular expression. So those are the two ways you can make it. Yeah, there's a one-to-one. Yeah. And then it looks at the version control information, the update line, to see who's checked in code. Now, sometimes you'll get some false positives here. I mean, you can't narrow it down. If 12 people check in code all at the same time and one test starts failing, they'll all get the email. But they quickly point the finger at the other guy and figure out it wasn't me. So you have like one test that runs. Mm-hmm. Right, but do you run it as one big executable? Right. Mm-hmm. Yeah, it'd be good things to look at. And I believe there have been some people that have done the Google test integration with CTest. I don't have slides on that right now, but it's been done. But yeah, that's great. Great idea for future work. Yeah, a lot of times we have, like in ITK, we create one test executable for it contains the ability to run lots of tests, but then we just run it multiple times for each individual test. But I suppose I guess the danger of running them all at once, if there's a crash, you pretty much lose. posted one. I talked about that. So a little overview of the CDash testing. We've got Purify, Valgrind support, coverage support through GCov or Bullseye. This next bullet's sort of a thing to think about. You want configuration coverage. It's not necessarily part of CMake or CTest does this automatically for you, but if you look at our dashboard, you can see we're testing. Almost all of our builds have spaces in the paths, because that always seems to trip people up. And if you're doing a build system, you definitely want to be testing that. And then you also want to be testing different versions of OSs. I've got a stack of Mac Minis. Every time there's a new version of Mac comes out, I buy another Mini and stack it on top of the stack and run the nightly tests with that. And then there's making sure you're covering all the libraries and options within your code. And then this final one, CDash, it doesn't have support for actually doing the image differencing, but it can support, you put some XML markup in your output of your program to tell it that, here's a base test, here's the image I got, and here's the difference. And then CDash can display that online. And this has been going on with VTK since, a long, decade or so. And we found out early on that, all OpenGL implementations are not created equal. They're and sometimes validly different. So it supports, you might have something triangulates one way and something goes the other way, and it shows up as an image difference, but it's really not a failed test. So we can support multiple valid images. Okay, the final part of the talk is CPack. Sure. Okay, great. Mm-hmm. Right now it's serialization on one and using the cores, although we test things like ParaView, which use MPI, but it runs MPI launch to run those tests. But we've done some experimental work with hooking together with some of these batching systems for the supercomputers. So if they want to test something on a supercomputer at Sandia, they need to basically you have to schedule it. You can't just run it. So we've got some basic support in there for that right now. It's in the development branch. It's not in any release. But the idea there is you could specify some tests and have it batch them off, and then it sits around and waits until they actually get results and then collect them up. So we're working on that, but there's nothing actually in a release. Yeah. All right, so I'll go on to CPack now. All right. So CPack is bundled with CMake, and it creates professional-looking installers. Platform-specific, again, it takes the same model as CMake. It's a meta installer tool. We use Nullsoft on Windows, and we can create tar.gz files. You can also create OSX package maker, RPMs, Debians. And again, this is this thing that a lot of developers, I remember early on at Kitware when we wanted to release a CMake, there was like one guy, he's the guy that knows how to run our installer system. If he's not around, you can't make a release. It was one machine that knew how to do it. And again, this sort of takes that and gives it to developers in a much easier way if they know how to write the install rules for CMake in their project, then they can write a nice installer. And it also supports component-based stuff, so you can do the typical stuff of install with or without headers, with or without libraries, that kind of work. And there's a wiki page talking about how to do the component installers. Using it on Windows, you'd install the command line zip program or Nullsoft installer. And then inside your project, you set some CPack options, variables that you need. You include the CPack module, and then it'll reuse your existing install rules. And then running it, you can type make package or make package source. You can run CPack and give it a configuration file and tell it to do Nullsoft or zip. It's fairly easy to use. There's some more information about CPack in the book and in this wiki page. And finally, I wanted to sort of end with a real simple example. This is a Qt example, and it's fairly short. So it basically says up at the top, I want version 2.8 of CMake or greater. And I'm saying project hello Qt. And then I'm saying find required dependencies. I say, find package Qt required. And then I add an executable. And right here I'm saying it's a Win32 executable, so it doesn't pop up a console. And it's also a Mac OS X bundle, because that's what the Qt thing's going to be. And here's my source file. And then I'm saying target link libraries to the target name, the executable, hello.qt. And I want to link in the Qt main library plus the Qt libraries. And then I'm going to install it. So I'm going to install targets hello Qt, which is the name of the executable, to a destination directory of bin. I'm going to include this install system required libraries, which will, on Microsoft, pull in the required runtime library plus the manifest, side-by-side manifest stuff that you need. And then I'm setting a version for my project, 1.0. And then finally, I'm saying that I want to package this executable, hello Qt, and I'm going to call it hello space Qt. And then I include CPack. And now, I think, to me, this is pretty cool. And this next one is same thing, except now I want to use boost inside my Qt, because I'm going to try the boost signals instead of the signals and slots from Qt. And to do that, I need to add 4 extra lines into the project. Basically, I'm telling it to use the static boost. This is because the binary from Windows. The binary from Windows is for boost comes as a static library, and I'm saying I want boost required, and I want to make sure it has the signals library built with it. And then I'm going to include the boost include directories, and finally I'm going to link the boost libraries to the target. And then the rest of the stuff's the same. So now I've got something to use Qt and boost, and it'll work on Mac and Windows. So and if you tried to do that, with Makefiles or Xcode projects, it would probably take you a lot longer, I would imagine, potentially. Finally, this is a slide. One of the hot areas of research at Kitware is informatics visualization. So we're actively working with Sandia. Most of our history of visualization is looking at things that sort of make sense on the screen, like a CT scan. You look at that, you look at the visualization of it, you go, yeah, that's the inside of somebody. You look at this thing over on the left, you go, what if I want to look at a class hierarchy? How do you visualize that? And this is probably something that happens at Google all the time. But we're working on that, and it also in a scalable way, so it'll work on supercomputers and things like that. But the idea here is maybe we can leverage some of this into the dashboards or testing. We're not sure really where it's going, but that's the general idea. So in summary, I talked about CMake, the build tool, and testing with CTest and CDash, and finally deploying your software with CPack. And there's some links to kitware.com, CMake.org, and CDash.org. There's my email. I'm always happy to answer email. I love reading email. And thanks for your time. But I got one more thing I want to do. I was going to do a quick demo here. So I'm going to drop out of PowerPoint. But this is the last slide in PowerPoint. And let's see if this works. Do a live demo. So I'm going to I've got that example Qt that I talked about with Boost. And yeah, of course, it's too big because I had to change the resolution on my screen. So we'll configure. And we'll pick, we'll try Visual Studio 2008. And it's testing the compiler down here. It's checking the compiler ABI. It's found Qt. It's found Boost with signals. You can see it found my open source build of Qt. I can look at an advanced view. I can look at a group view so we can see, let's see, what did it find with Boost? It found program files Boost 3.8. It found the library directory for Boost. Get the idea. We'll configure again. We'll generate. And then And I'm in example qtb, which is this directory here. Pop up the solution. Oops. Build it. And then I'm going to package it. And it's running nullsoft for me. And this is the same source code as CMake that I just showed in the slide. Got 0 errors. And if we look here, lo and behold, we have an installer. It's pretty minimal. It's got some defaults. We'll install it into hello Qt. And we're done. And then if we look over here, there we are, and it's highlighted because it's new. We run it, and we get hello world. Yay. And we'll throw this slide up one more time. And now I'm done. So any questions? Or? Well, there's a big example out there if you want to look at one is KDE. I mean, that's probably one of the largest open source efforts out there. It's probably a couple million lines of code. Yeah, you do set something, set library sources, and you'd give a big list, and you could, put some conditionals in, if Apple include these, that type of thing. Usually in really, really large projects, you can create macros or functions in the CMake language, and they have like, an add KDE library, and it might do some extra stuff for you. But it does scale into really, really big projects. No. Yeah, no. It would be something more like, I could, I don't know if, let's see if, this isn't a huge project, CMake itself, but so there's sort of a source list. So I'm saying set sources, and I'm listing them out. And then right here, so I've got this elf sources, which is an optional thing. So if I'm on Windows, I don't have the elf editor. But it's got each line, so it wouldn't get conflicts every time. And then here I'm adding, if I'm in Unix, I'm going to do Kdevelop. And there's some Apple sources for doing the Xcode generator. And there's the Visual Studio stuff. So, sure. Good question. Probably should modify the slides to show more complicated things as well. You want to show it's easy to use, but it also scales. Yeah. No, we don't. CMake's got to be around. We're using it for the copy commands. We're using it for the installer. It's like the install rules, cross-platform installing. It's a CMake command that's actually running to do all that work. So there's a lot of infrastructure that you really need cross-platform. So then you end up saying, all right, well, you don't have to have a build tool around. We can do Visual Studio projects, but you have to have Python because we got to do all this other extra stuff anyways. So the idea is to have a minimal requirement, which is the C++ compiler. That was our take, 10 years ago when we started this. And I'm still standing by it. really well. I mean, I think when KDE went over, the build times went significantly down from their AutoTools builds. KDE, they use a build farm and stuff, so it's a couple million lines of C++ type thing. They're using dist.cc, I think. You just set the compiler to be dist.cc and then run CMake. Right. Depending on what you do, I mean, yeah, it depends on the size of the project and how many try compiles you're doing. So if you go crazy with checking for every possible header or whatever, it can get slower. But it only does it once. So yes, yes. No, they've all been cached. Yeah. Yeah. Yeah, it should be under a minute, I would think, on a reasonable machine. Like the Trilinos project takes about a minute or so. It's like 42 packages, and each one has several libraries and executables. So it's probably something along that scale. Depends on the computer and all that, but we do try to make it as fast as possible. Yeah. But yeah, we spend a lot of time optimizing it whenever we get a chance. I think we're about done then. Yeah. Thanks for inviting me. I had a great time.